Alright, so we had defined diagonalizity in the last class. We gave examples to show that some matrices are not diagonalizable. We also had this theorem there in some sense, we didn't write it, that A is diagonalizable if and only if A has n linearly independent eigenvectors. I didn't state it, so let me write this as a statement theorem. A n cross n, then A is diagonalizable if and only if A has n linearly independent eigenvectors. So, this we had proven using writing the matrix P as eigenvectors u1, u2, un and so on, all right. So, I will just stop that part I hope you have understood, think about it again. Now, so the next thing that we would like to do is that when can I find linearly independent eigenvectors? So, the question, what are the conditions under which we can hope to get n linearly independent eigenvectors. This is what we need. All right. So, that we'll get to that after a bit or after some time. What we want to say is that we have till now looked at examples where the diagonalizity has failed because of the eigenvalue being the same in some sense, fine. So, what we would like to say is that if I pick up eigenvalues which are distinct, look at the corresponding eigenvectors, can I say that they are linearly independent? So, the next thing that we would like to say is that if alpha 1, alpha 2, alpha k are distinct eigenvalues, fine, and you have corresponding eigenvectors u1, u2, un, uk, can I say, so these are eigenvectors, fine. So, what we know is that alpha 1 u1 is equal to a u1, similarly a uk is equal to alpha k uk. So, these are eigenvectors, alpha is are distinct. Can I say that this will imply that this set u1, u2, uk is linearly independent, all right. So, what we are saying is that the eigenvectors corresponding to distinct eigenvalues are linearly independent. So, we are saying eigenvectors corresponding to distinct eigenvalues are linearly independent. This is what we are claiming here, all right. So, let us try to prove it. So, proof, fine. So, if I want to prove that this is linearly independent, I am supposed to form a system of equations. So, let us form a system of equation. So, consider the system C1 U1 plus C2 U2 plus Ck Uk, all right, is equal to 0. In the unknowns C1, C2, Ck belonging to C, complex numbers, because Ui's are complex vectors, all right, and I am assuming that A is n cross n, and these are, so Ui's are in Cn, fine, so that it makes sense. So, I am solving the system C1 U1 plus C2 U2 where the Ci's are unknowns, I want to find them, or since I want to prove that these are linearly independent, the eigenvectors are linearly independent, all right, I have to show that the only solution here is the trivial solution. To show there is only the trivial solution, all right. So what we can do is that we can multiply this matrix, this vector equation, by certain matrices. All right. So let us try to multiply this by something. All right. So I want to multiply this by, say, A minus alpha 1 I. I want to multiply this star by this. If I do that, what do I get? On the left hand side, I will get this times 0 is 0, fine. The other side, I will get it as A minus alpha 1 I times C1 U1 plus C2 U2 plus CK UK. Now what it gives me is, just put inside C1 times A minus alpha 1 I U1 plus C2 times A minus alpha 1 I U2 plus CK A minus alpha 1 I UK, fine. This is what I get. Now this is equal to, now what is U1? U1 is an eigenvector corresponding to alpha 1, or we already wrote here that A U1 is equal to alpha 1 U1. So if I use this idea here, what do I get? I get A U1, if you rewrite it, it is A U1 minus alpha 1 U1. So therefore this part tells me that this is a 0 vector. So what I get is here C1 times 0 plus C2 times something that I am not bothered about for the time being, that we will write afterwards, plus CK times something here. Is that okay? So by multiplying by this here, all right. So by multiplying by this A minus alpha 1 I have been able to get rid of C1. Is that okay? So C1 has lost. So what I have got now is that earlier I had equation which was in C1 C2 CK. Now I have equation only in C2 times something plus C3 times something plus CK times something. So the number of variables or unknowns has reduced, fine. This is more important. You are trying to again go back to your Gauss elimination method, where at each step we have tried to reduce the number of unknowns. So we removed C1, now I want to remove C2, fine. If I want to remove C2, what we need to do? I need to, so if I want to remove C2, I need to multiply A minus alpha 2 I to the first equation or to this equation, all right. Because what I know is that if I multiply this, then A minus alpha 2 I of U2 will give me 0, fine. So I need to multiply by this, but I cannot multiply to the first one. The star cannot multiply to a star as C2 will not appear, but C1, C3, C4 till CK will appear, all right. So will appear. So what happens is that I can kill C2, but I cannot kill C1, all right. So that's the problem. So what I would like to understand is, can I do this itself, multiply this to the equation that I have got here, which is, say, double star for me, all right. So let us write the double star again. So double star is nothing but 0 is equal to C2 times A minus alpha 1 I times U2 plus so on plus CK times A minus alpha 1 I UK. This is what I had, fine. Let us multiply A minus alpha 2 I to this. So if I do this, all right, if I do this, and also you observe here that, which is very, very important observation, that this matrix times this matrix is same as A minus alpha 2 I times A minus alpha 1 I. That is, these two matrices commute. So this and A minus alpha 1 I, they commute. Why do they commute? Because I am just multiplying by A itself and by identity. Identity commutes with everything. The scalar matrix alpha 1 I or alpha 2 I, they are scalar matrices, they commute, all right. So I would like you to check that they commute here, and therefore I can just write this as 0 times C2 of A minus alpha 1 I times A minus alpha 2 I U2, and so on. I can go on. plus Ck times A minus alpha 1I into A minus alpha 2I UK. If I do this, what will happen is this has become 0 now. I will be left out with 0 is equal to C3 times A minus alpha 1I, A minus alpha 2I, fine, times U3 plus so on plus Ck times A minus alpha 1I into A minus alpha 2I times UK, fine. So, this is what I will be left out with, this is what you have to understand, fine. So, in general what I am doing, let us rewrite this in a nice form so that you understand it, fine. So, I would like to write these matrices. So, I want to write some matrix. So, I define T1 is equal to product A minus alpha I of identity, I is equal to 1 to n divided by A minus alpha 1 of I. So, this one comes with this one for me, is that okay? So, I am defining my T1 like this. Similarly, I can define T2 as product I is equal to 1 to n A minus alpha I of I and then divide by A minus alpha 2 of I, fine. So, if I look at this, what I am trying to say is that this corresponds to looking at A minus alpha 2I so on till A minus alpha k of I. This corresponds to looking at A minus alpha 1 of I, then A minus alpha 3 of I, alpha 2 of I is lost here, not there, and then I am going all the way to A minus alpha k of I, fine. And what we know is that these matrices commute, they commute here, fine, because I am just multiplying A with identity, so they commute. So, if I multiply, T1 to C1 U1 plus C2 U2 plus Ck UK, what I am doing is I am multiplying this. So, this was T times 0, which is 0. So, what I am doing here is that I am looking at C1 times T of U1, T1 of U1. So, let me write C1 into T1 U1 plus C2 times T1 U2 plus Ck times T1 UK is 0. Now, what is T1 U1, what is T1 U2 and T1 UK, fine. So, understand this very nicely, this is very important idea. So, if I want to look at T1, T1 has A minus alpha 2I, it has A minus alpha 3I, it has A minus alpha ki, fine. They commute. So, at some stage, since they commute at some stage, if I multiply this with U2, this will give me 0, all right. Again, when I multiply T1 with U3, so T1 with U1, I do not know what that will be, but what I know is that T1 with U2 will be 0, because there will be somewhere where A minus alpha 2 of I will come. Similarly, T1 of U3 will be 0, basically because A minus alpha 3 is there. So, what will happen is that all of them T1 of UK will be 0, all right. So, all of them they will be 0. I do not know whether this will be 0 or not. So, we are claiming now, that T1 of U1 is not 0. That is more important, that we are saying that it is not 0. We have already shown that T1 U2 is 0, U3 is 0, UK is 0. So, what we are saying is that this is already 0, T1 U2, this is already 0. The only problem is that whether this is 0 or not. So, let us look at that part. So, what our T1 is, T1 had these terms. So, the first term was A minus alpha 2I, then there was A minus alpha 3I and so on, A minus alpha k of I. I am supposed to multiply this with U1. If I do this, then what I get is that this part, if I indicate, I just leave it as it is for the time being. Now, this part gives me A1 is nothing but alpha 1 U1 minus alpha 2. So, it will be alpha 1 U1 minus alpha 2 U2, this is what I will get, just multiply it. AU1 is alpha 1, so this is nothing but AU1 is alpha 1 U1 and then alpha 2 U2. So, I can write it back as things like this, and this is alpha 1 minus alpha 2 of U1 again, this was a u1 here, alpha 2 of u1, all right, fine. So, again this is a constant, so I can just put alpha 1 minus alpha 2 outside here. So, then I will get here a minus alpha k of I, so on till a minus alpha 3 of I times u1. Again this will give me, just multiply it out, you will get here alpha 1 minus alpha 3 times u1. So, at each stage what I am getting is that we will just get it. So, if I do the whole calculation, what I will get is that I will get alpha 1 minus alpha 2, alpha 1 minus alpha 3, so on till alpha k minus alpha 1 minus alpha k of u1, all right, fine. And we have taken that the alpha 1, alpha 2, alpha k are distinct, and this implies that alpha 1 minus alpha I is not equal to 0 for all I greater than equal to 2, and therefore, this vector is not 0. Is that okay? Fine. So, that is what is important, that all these vectors t1 u2 is 0, t of t1 u3 is 0, and so on till all of them are 0. Only vector that is left out is this part. I know that t1 of u1 is not equal to 0. So, what I get from here is that c1 times some constant, which is this number, which is product of alpha 1 minus alpha I is equal to 2 to k times u1 is 0, fine. u1 is a eigenvector, so that is not 0. This is not 0 because alpha i's are distinct. So, it implies that c1 has to be 0, all right. So, we have shown that. Now, if I look at this part, we have shown that in this part, that in this linear combination, if I look at this linear combination, c1 is 0 we have shown. So, shown c1 is 0 by applying t1, all right. I can apply t2 again to the whole thing to get c2 is 0 and so on. So, let me write that now. Applying t1 to c1 u1 plus c2 u2 plus ck uk is equal to 0 implied c1 is 0. If I apply t2 to the same thing, I will get c2 is 0 and so on. So, applying finally tk, and what was tk? If you remember, tk is nothing but it is supposed to be a minus alpha k minus 1 I, a minus alpha k minus 2 I, so on till a minus alpha 2 I into a minus alpha 1 I. If I apply this matrix to this equation, I will get that ck is 0. So, the idea is that each of these matrices, they play some role as far as we are concerned. Is that okay? So, a minus alpha k of I applied to uk, or not uk, I will write uj, let me write uj here, uj, this is 0, fine. And if I am looking at a minus alpha j I of ui, this is not 0 if I is not equal to j, all right. That is very important, because of that we are able to get this. Is that okay? Generalization of this idea, let theorem, let alpha 1, alpha 2, alpha k be distinct eigenvalues of A with, I do not know about algebraic multiplicity, with geometric multiplicity of alpha I as n sub I, 1 less than equal to I less than equal to k. Then A has summation I is equal to 1 to k ni linearly independent eigenvectors. Is that okay? So, what exactly we have shown in the previous theorem was that if I have got alpha 1, alpha 2, alpha k, I had u1 here, u2 here, uk eigenvectors, one eigenvector. So, I took any eigenvector u1, u2, uk of alpha 1 to alpha k, then they are linearly independent. Now, what we are doing in this theorem is we are trying to generalize. So, what we are saying is that if I pick here eigenvectors as u11 till u1n1, because there are n1 eigenvectors here. So, n1 dimension of a minus alpha 1 I null space of a minus alpha 1 I is equal to n1. That is what our assumption is. So, I will get so many linearly independent eigenvectors. Here I will get u21, u22, u2n2 eigenvectors, fine, and here I will get ukn1, uk1, uk2 till uknk eigenvectors. So, what we know is that since dimension is this, implies that these are linearly independent. Here the dimension is n2, so these are linearly independent. Similarly, these are linearly independent. All right, fine. What we are claiming here is that all of them. So, what we are claiming here, that if I look at the set u11 till u1n1, u21 till u2n2, so on till uk1 till uknk, then this is linearly independent set of eigenvectors. This is what we are claiming. And the idea of the proof is, what I know is that if I just pick any one from the first set, any vector from the second set, any vector from the kth set, then that is linearly independent because of the previous theorem. All right. So, they are linearly independent because of this part, that if I have any collection of eigenvectors corresponding to distinct eigenvalues, they are linearly independent. So, if I pick u11, u22, uk2, so if I pick, so if we pick u11, u22, u32, so on till uk1, if I pick this collection, then this is linearly independent because of they correspond to distinct eigenvalues. All right, and hence all of them, they are going to give me some eigenvector or the other. This is what is given to me, they are eigenvectors, and since they are coming from distinct eigenvalues, they are linearly independent, and among themselves they are linearly independent because I chose them to be linearly independent because there are n1 of them here, n2 here and nk here. Is that okay? So, you need to understand that if I have distinct eigenvalues, I can do things. All right. So, as a corollary of this, as a corollary, let A be n cross n. If A has n distinct eigenvalues, then A is diagonalizable. So, you are saying that it has n distinct eigenvalues. So, n distinct eigenvalues means there will be n linearly independent eigenvectors, and what we saw was that whenever A is diagonalizable, if and only if it has n linearly independent eigenvectors. All right. So, this was same thing as or equivalent to saying that A is diagonalizable. Fine. So, what we are saying here is, so as a example or as an application of this idea, example, look at this matrix A, which is 1 2 3 4 0 2 1 2 0 0 3 5 0 0 0 7. All right. So, if I look at the eigenvalues of A, they are going to be 1 2 3 and 7 because this is an upper triangular matrix with diagonal entries 1 2 3 7. These are distinct, implies A has 4 linearly independent eigenvectors, implies A is diagonalizable. So, this is the power that we have, that as soon as we know that something is upper triangular, it has distinct entries on the diagonal, then that matrix is diagonalizable. All right. So, here I know it is diagonalizable, but if I want to look at this matrix 1 1 2 4 0 1 1 2 0 0 3 5 0 0 0 7, cannot make any statement, without doing proper calculation. All right. So I'll have to calculate thing here, because I don't have any theorem with me which will say that this is diagonalizable. This may be diagonalizable, this may not be diagonalizable, but you have to compute basically, because here the eigenvalues are 1, 1, 3, 5. So there is an eigenvalue which is repeated. Eigenvalue A1 is repeated. All right. So whenever we have that something is not repeated, everything is nice, otherwise there is a problem. All right. So that's all for now. Thank you.